We're starting with 3. So number 1 is very similar to what we covered in class, and it's just on the interval. You don't have to graph it. Just determine the max min. You don't have to find the second derivative, just the first derivative. I think that this is pretty straightforward. We can do that if we have time today. Okay, which ones do you want to start with? Okay, let's do the first one. So we have 2. So we have limit. X approaches 0 from the right. Sine x times natural log x. Okay, so first let's see what this is all about. Where does this go? Say it again. Very good. Where does this go? Before you say anything, you can always on the side check the graph of natural log. And this is extremely important. Yes, I know you can graph it with a graphing calculator, but these basic simple functions should not require you to go back to the graphing calculator, because we have a few that we should remember, like arctangent, like sine, cosine, tangent, e to the x. Good. So where does this go when x approaches 0 from the right? Negative infinity. 0 times infinity or 0 times negative infinity is the same type of situation. It's an indeterminate case. I cannot conclude. What do I do? So here's a hint. No, I cannot differentiate in the product form. I can only differentiate in 0 over 0 or infinity over infinity. And this is not ready yet. What I was going to say is this. Never bring natural log to the denominator. You will get in big situation if you do. So then I have to do something else. What else can I do?
Even sign.
Yes, Ricky, what did you want to say? No. We have a product. We don't have both sides here, Joey. This is just a product. We do the exact same algebraic trick as before. Because sine is in front as over 1, sine over 1. I just learned from Ashley that. Sine over 1, and we flip it and bring it to the denominator as 1 over sine x. I think that's a good explanation. Thank you. I learned from you. I said that a long time ago. Good. So now we try again. The numerator doesn't change. It still goes to negative infinity. But what about 1 over 0 from the right? Yes. Okay, now this I can differentiate. I really don't like to differentiate 1 over sine, but I have another function, another trig function. So this was page 8. That is 1 over sine. And I want to work with that. Yes, indeed. Thank you very much. Well done, Brayden. Yes, indeed. If it's 1 over s sine, it's cosecant. If it's 1 over c, cosine is s, secant. Very good, awesome. Good. Infinity over infinity, I like it. Not really, because of the way the function looks like, but that's what we have to deal with. The numerator prime is
1 over x.
very good. The denominator prime is negative cosecant cotangent. Okay, so now I have limit as x approaches 0 from the right. I'm going to change this into 1 over, minus in front, x cosecant x cotangent x. Because this is over 1, and I flipped it. And now let's see each and every piece where it's going. Where is this going?
0.
Perfect. Where is this going? You can say, I don't know, I can think in cosecant terms. But you can think in, or you can change this, if you'd like, into 1 over sine x and bring sine x to the top, if that's a better idea. Cotangent is cosine over sine x. So we can do that first. Let's do that. So limit as x approaches 0 from the right, and I multiply and I flip. So I have negative in front sine squared x over x cosine x. This is just because it's easier to think in sine and cosine versus cosecant and cotangent. Always go back to basics. Okay, so now, if you remember, limit as x approaches 0 from the right, negative sine x over x times sine x over cosine x. So I'm hoping that by now you will understand, or you already know, that all these, yes, Vanessa?
I understand why, like, how cosecant x goes to 1 over sine x and how cotangent goes to cosine. I don't understand how you got that next equation though.
I flip the denominator. So whenever I divide by a fraction, I flip the fraction. So I get sine squared at the top over x cosine x.
Okay.
So the numerator is 1 over 1, but this denominator is x times 1 times cosine x over sine squared. And then I flip it as sine squared over x cosine x. So maybe I should write it like this first. 1 over x times 1 over sine x times cosine x over sine x. And as the next step, 1 over x cosine x over sine squared. And then it becomes sine squared over x cosine x with minus in front.
Okay.
Is that better?
Yeah.
Thank you. Sorry about that. Okay. This I know. Oh. 1. Very good. Thank you, Chris. Where does this go? Indeed. Indeed. Tangent. Cosine goes to 1, sine goes to 0. So the limit is? Very good. Indeed. The limit is 0. Please, this is a special case. Please do not conclude ever that now we know 0 times infinity is 0, because we don't. It's an indeterminate case. Anything can happen. Very good. Any questions on this? Do we remember this limit? This one that I'm shading in right now?
Yeah.
Okay, as long as this and this and this are the same, and 0 or from the left, from the right, or 0 from either side, then the limit is 1.
Can it be infinity or does it have to be 0?
It must be 0.
Okay.
Let me write that limit one more time. So it's limit when the box approaches 0 from sine of the box over the box equals 1. And we also proved it at some point in time with L'Hopital's rule. Yes, Ricky?
Is it only a sine?
Only with sine and also reverse. X over sine. Yes, only with sine. Because if I put cosine in here, the numerator will be 1 and the denominator will be 0. So we are looking at the second one? Yes?
Yeah.
Any questions? Other questions on the previous one? Okay, limit as x approaches infinity, e to the x plus x raised to 1 over x. We have looked at this problem in class. So I'm hoping that between now and you take test 3, you are going to look at those problems in class, please. Okay, what is this? Where does this go?
1.
0.
Oh,
Good. Where does this go? Very good. Where does this go? 0. This is not a nice situation. It's a power. So the power is always the most involving. The product is easier. The ratio, 0 over 0 or infinity over infinity, is the best. The product is okay. The difference, infinity minus infinity, okay. This is the ugliest one. What are my chances here? Remember power, the word power. we have to apply law. Whenever we talk about something like this, thank you. Your extra credit went up. By -3. No, just kidding, just kidding, just kidding. Yes, indeed, we have to start with naming the function y. Then, next step, yes?
Don't we
Yes?
move the limit to the left of natural log?
Yes, but not yet. Not yet. Yes, eventually we will, absolutely. Yes. Can anyone dictate the next step? Yes.
Put a negative sign on the exponent.
Because I said negative, so I can't talk about negatives because I'll have to write it. Thank you. Sorry about that. Okay, ready? What is the next step?
Natural log y equals natural log e dx plus x. Then
Excellent. So since we know that, I already brought an a 1 over x in front. Okay, I'm happy now. What should I do next? Every time I don't make an error and I don't write a minus out of the blue, I'm happy. What do we do next? No, not yet. I can never differentiate. Very good point. I can never differentiate unless it's inside the limit. Unless I graph or find maximum or something, I don't differentiate. Apply the limit to both sides. Excellent. So I have limit as x approaches infinity from natural log y equals limit as x approaches infinity from natural log e to the x plus x over x. However, initially it looked rather difficult, but now what do you notice? You notice that the top goes to and the bottom goes to. Pretty straightforward. So then, limit as x approaches infinity from the top.
1 over e dx plus x.
Excellent.
Minus e dx minus plus 1
Excellent. Over,
x squared.
over.
One.
Yes. So let me go back. Inside a limit, the ratio is differentiated not as a ratio, but only inside the limit. We differentiate the top by itself and the bottom by itself. Only inside the limit and only when we have 0 over 0 or infinity over infinity. Is that okay? Good. So now the next step is limit as x approaches infinity from e to the x plus 1 over e to the x plus x. Ready? So the top goes to, the bottom goes to, yes, Ricky?
Didn't we move the EX plus X to the denominator?
I can't because the power is positive.
So how do we fit EX?
Because I divide by 1. So this is over 1. 1 times this over this times 1 is this over 1. Is that okay? Better? So then limit as x approaches infinity, the top,
E dx
the bottom.
e dx plus 1.
Very good. Okay, infinity over infinity. Limit as x approaches infinity, the top,
E dx
the bottom.
e dx.
Okay, what is the answer? Excellent. Now remember what we do. We copy the beginning and we copy the end. So limit natural log y as x approaches infinity is 1. And now we're ready to think. And we will apply, yes, Vanessa?
Why did you do that twice? I don't understand why.
You mean from here, here?
Yeah.
Because I still don't know what e to the x over e to the x plus 1 is.
So where did
Well,
the
I
one,
do know, but
where did the one go? Like
how much is 1 prime?
What did you?
Yeah, because it's infinity over infinity, I applied L'Hopital's rule 1 more time.
Okay.
Yes, till I completely cleaned it up of everything. Because here I cannot simplify. I cannot simplify to the x raised to the x because there is an extra term in the denominator. So I had to differentiate one more time. Okay, so now we're going to apply a method that allows us to determine the limit only because natural log of this, yes, Ricky? Go ahead.
Switch the upper.
Yes, because natural log y is a continuous function. Basically, y is a continuous function, natural log will be a continuous function. Only in that situation we are allowed to swap the operators. So this goes in front. So this is natural log. A limit as x approaches infinity from y is 1. And now I'm asking myself, what could that be? And there is only one answer. E indeed. So limit as x approaches infinity from the original function, which was e to the x plus x raised to 1 over x, is e. You never knew that 0 to infinity will turn into e. Yes? Vanessa? Because natural log of e is 1.
Okay, is that just like a number?
There is no other number whose natural log is 1. Yes, so natural log e is 1. So therefore, this limit must be e. Very good, good pick. Excellent. Next, what would you like to look at?
Maybe 4 or 5.
Say it again.
4 or 5.
4 and 5. Good. 4 is pretty similar to what we covered, but let's do 4 and then 5. So we have f of x equals 2 the square root of x minus x. Okay, we're asked to determine everything and graph the function. And I'm ready when you are. How do we start? Very good, awesome. I don't have enough room here, so I'm going to go to the next page with a table. Yes, I'm ready, please. What is a domain? What do I have to write and solve? Or just write?
Set that includes 0.
No.
Like negative infinity.
No, it's a square root. Say it again. Very good, excellent. So the domain is 0 to infinity. Very good. Is that clear why? One more time. Is that clear why? The quantity under the square root must be 0 or positive. If the quantity under the square root is negative, then the function is not a real function. Good. Next step. X-intercepts. How do I find the x-intercepts?
Set the whole equation.
Very good. 2 the square root of x minus x equals 0. What do I do now? And no, we don't need to think in terms of the Newton's method. It's much easier than that. So what would you do? Say it again. It's not going to be any. It's not going to help. It's not going to hurt, but it's not going to help. So what can I do? It's a radical equation. I need to separate the radical from the rest. That's the very next step. 2 the square root of x equals x. Now what is the next step? Of course. So I have 4x equals x squared. Is everyone with me? Let's stop for a moment. Is this clear?
Yeah.
Radical equation, we separate the radical from the rest, we square both sides, and we get this quadratic function. And then we have x squared minus 4x equals 0. We will factor x, and we get two options, 0 and 4. Because we squared, we have to go back to the equation, make sure that these work. 0, yes, I checked. 4, yes, I checked. And now I go back to the table. I put 0, yes, the X-intercepts. There is no point in plugging 0 to find the Y-intercept because I already have it. When I plug in 0, I get 0. One more step, last step is right here. I have to find the limit of 2 the square of x minus x as x approaches infinity. Where does the first term go? Very good. Where does the second term go? Right. But this is not that situation. How come? You could say infinity minus infinity is an indeterminate case. True. However, let's look again. Which one is the most powerful? Is the x raised to 1/2 or x to the first power is more powerful? They're not as powerful. One of them goes to infinity much faster than the other one. So x is the most powerful one. So when x approaches infinity with minus in front, this is so much smaller that it would not affect the outcome. So what is the answer then? Indeed. As you know, we will very easily determine or find our mistakes when we determine the first derivative. We are done about the function. There is nothing else I can find about the function from the function itself. We are ready to differentiate. So I'm copying the function here. And let's differentiate. F prime of x equals 2 times. Excellent. Minus 1. Great job. Thank you. So this is 1 over the square root of x minus 1. But I need the least common denominator because I'm getting ready to find what?
Critical number.
Excellent. I'm ready to find critical numbers after this. What is the least common denominator? Great job. What do I multiply this by? Of course. Great job. 1 minus the square root of x. Good. So now I'm trying to find critical numbers. And they come from 2 sources. Possible sources. F prime of x is 0 or f prime of x equals undefined where the function is defined. So first of all, where is this undefined? Yes, but I'm not interested in less than 0. I'm interested in 0. So this function is undefined at 0. The derivative is undefined at 0, so the first and the second derivatives will be undefined at 0. Good. So now I'll set equal to 0. Which piece could be 0 if the fraction is 0? The numerator. Very good. So then I have to solve the equation 1 minus the square root of x equals 0. Again, this is a radical equation. How do I treat it? Good. The square root of x equals 1. I square both sides and I get x equals 1. And that is the only critical number. 2 critical numbers, but one is x equals 0. The only critical number coming from f prime being 0. That's what I meant to say. Very good. So this is 1 and 0. We are ready to study the sign. So let's copy the first derivative here. 1 minus the square root of x over the square root of x. Which piece of all this you will waste, or we will waste our time if we try to plug in?
No,
Exactly. That's always positive, disregarded when it comes to the sign. So now let's plug in a number like 4 to the right of 1. Square root of 4 is 2 with minus in front, negative 2. 1 minus 2 is? Let's plug in a number to the left of 1. We can plug in 0 because it's about the top, not about the bottom. When I plug in 0, I get 1 minus 0. If I plug in 0.25, I get 1 minus 0.5. So it's still positive, no matter what I plug into the left between 0 and 1. I have to determine this point. Where do I plug in to find this y value? In the function. Very good. So let's plug it in. So 2 times 1 minus 1.
1.
1 indeed. So I have 1 comma 1. Perfect. Now the moment of truth. I'm holding my breath just to make sure that I don't have to go back and check anything. Okay. From 0 to 1.
Increase.
Is that supported by the sign of the first derivative? Very good. From 1 to 0.
Decrease.
Is that supported by the sign of the first derivative? From 0 to negative infinity. Is that supported by the sign? Okay. Good. So now we find the second derivative, and then we are ready to graph. Where is the first derivative? Okay. This is what I like for the first derivative. This is what I'm going to copy. So the first derivative is x to negative 1/2 minus 1. This is what I want to differentiate. So I changed 1 over the square root of x into x to negative 1/2. Why? Because it's easier to differentiate. Yes.
And why you only do the numerator?
Because I changed the power into negative. So this is 1 over x to 1/2, and I change it into x to negative 1/2.
Why wouldn't you use the other one?
This one?
It's harder. Yeah.
It will take me 5 or 10 minutes
Okay.
to differentiate that one. It would take me 5 seconds to differentiate.
Okay.
So the second derivative, negative 1/2, x to negative 3/2, which is negative 1 over 2 the square root of x cubed. Okay, the second derivative is or is never 0.
Never 0.
Awesome, never 0. If it's 0, the numerator has to be 0. There is no variable in the numerator. Excellent. Which of this, well, I'm not going to waste my time to plug in? The whole thing. And this is always less than 0.
Why?
Because I have x from 0 to infinity. When I plug it in, it's cubed. When I take the square root, it's positive. When I multiply by 2, it's positive. All this piece is positive forever in this function. So it's negative in front. Okay, here it is. No inflection points. I didn't even talk symmetry because the function is defined on 0 to infinity. It will be a waste of time. There is no symmetry here. Ready? We only care about the table, and everything happens from 0 to infinity. We don't care about the negative side. I will plot 3 points. 0, 0. I will plot 1, comma 0. And I will plot 2, 3, 4, comma 0. I forgot to ask, my apologies. What type of point is 1, comma 1? Excellent. Because the derivative is either undefined or 0, and it changes sign from positive to negative. Excellent. Well done. So, starting from 0, 0, increasing to 1, 1, opening down at all time. It reached the maximum, it will continue crossing at 4, 0, going to negative infinity. And this is the function to the square root of x minus x. Any questions? Any questions? I think from all the problems we looked at and the graphs that we graphed, I think we are pretty comfortable now with graphing and putting together the first derivative, the second derivative, limits, blah, blah, blah. How do you feel? A little bit better? Yes? Okay, very good. So let's look at 5. Any questions for me before we look at 5? Yes?
So the previous problem,
Yes?
how come the double,
Yes?
how come it's equal to zero?
Fraction is zero only when the numerator is zero. Well, 1 cannot be zero. It will never be zero. So whenever we have a fraction, like a over b is 0, this happens only if a is 0. But if I have a fraction like 1 over x equals 0, this could never be 0. Better? Very good. We have 1,200 centimeters squared of material, and it's available to make a box with a square base and an open top. Find the largest possible volume of the box. How do we address this? Where is the starting point? We did this problem in class, but we should do it again. Where is the starting point? Okay, so let's write the volume. What is the volume of this box? Area of the base times, very good. So it's x squared h. Good. Now this is the surface area. This is the material we used to build the box. So what is given now? What is 1,200 centimeters squared? Very good. Or A. Perfect. Area. So let's determine the area here. So we have an x squared, and we have 4 sides that are equal in area. 4x h. Perfect. And we are given that this is 1,200. What do I need? Yes, please.
Why is it 4x? I was thinking how you got that x squared plus 4xh from the.
Very good. So let's look at this box. So the volume of this box is the area of the base times the height. So assuming that it's square, this is not square, right? The base is not a square, it's a rectangle. But assuming it's a square, I have x times x, so it's x squared times the height. That's the volume. So now the question is, what is the area of the box? So I have this, which is x times x, which is x squared. But this piece is x times h. And this piece is x times h. This piece is x times h. And this piece is x times h. There are 4. And all 4 have the same area because the base is a square. Here, these 2 will have the same area, and these 2 will have the same area. But in our problem, all of them have the same area. X times h, x times h, x times h, x times h, and therefore.
So if it was, this one's with no, an open top, so if it was with an open top.
I would have added another, and it would have been 2x squared. Correct. Okay, so then what do we do next? From this equation, we will extract, exactly, we want to extract h. So we're going to subtract and divide by 4x. So 1,200 minus x squared over 4x. That's exactly what we wanted to do. Why? Because the function that we are discussing and we are interested in has 2 variables. We can't handle 2 variables. We have to eliminate one. And we will eliminate one by replacing h by what we have. So the volume now I can say is indeed a function of x only. So I'll multiply by x squared, and I have 1,200 minus x, bless you, over 4x. And I'll simplify by x, and I will have to distribute. But I will not distribute the 1/4. So I have 1,200x minus x cubed. If you want, you can, and rearrange it. Negative 1/4 x cubed and plus 300x. And this is not a difficult function to work with. It's cubic. It's not rational, radical, or log, exponential. Okay, so one more time we were asked to find the largest possible volume of the box. So it's available to make a box and find the largest possible. So what am I asked to do? Yes?
Where's the X cubed one?
So x times 1200 and x times negative x squared. Because this is outside and I have to distribute it to both at the top.
Okay, why'd you put it outside though?
It was outside. It was this x squared.
Oh,
This was
okay.
outside,
Okay.
and I replaced h by this.
Okay.
Better?
Yeah.
So I have a function. I'm happy now. The function is here, but what am I trying to find? I'm trying to find its max. Therefore, I need to find, yes?
When you're doing v as a function of x,
Yes.
where does the h go?
So we solved this equation for h, subtracting x squared and divided by 4x.
Yeah.
So then I went back to the volume and I replaced h in the volume by 1200 minus x squared over 4x, and I multiplied by x squared. So here's the x squared and here's the h.
Okay.
I just copied it from here. Is that better?
Yeah.
We simplified 1x and I only distributed 1x left. So it's 1/4, 1/4 times 12x, 1200x and minus x cubed. And then I put it in the correct order and I distributed 1/4. 1/4 times this and 1/4 times this is 300x. Is that better?
Yeah.
Very good. So what do we need to do next?
Find the critical number.
Very good. So we have to find v prime, which will be negative 3/4 x squared plus 300. Of course, this function will always be defined. There is no such thing as a volume, as a cubic function not to be defined. This is a quadratic function. It's always defined. So, but v prime could be 0. So then I have negative 3/4 x squared plus 300 equals 0. I have to multiply everything by 4. Negative 3x squared plus 1200 equals 0. And I get that x squared equals negative 1200 over negative 3, which is 400. Nice. And I take the square root. I should write plus or minus. However, x is the length of the side, so I'm not going to put, and this was in centimeters. As we discussed many times, remember, this is not sufficient. I cannot say, here, when x is 20, this will be the maximum volume. That's not sufficient. And this time we are asked, find the largest possible volume. So this time we have to plug it in. So we have to find this number. However, I don't know if this 20 gives a maximum or a minimum. I don't know. Well, so let's go back. When I plug in 0 on this side of 20, when I plug in 0 in the derivative, what sign do I get?
Positive.
Indeed. When I plug in 100 on this side of the derivative, what do I get? Yes, because it will be 100 squared is 1,000 times 3. Negative 3 will cover this. So it will be negative. What is this typical of? A max. But now they want us to find it. So we have to find v of 20. So this was v of x. So here's v of 20. Negative 1/4 times 20 cubed plus 300 times 20. So negative 1/4 times 8, 1, 2, 3, right? And then plus 6,000. So this is 2,000. I got 4,000 cubic centimeters. Correct me if I'm wrong, please. That's always the case. I got negative 2,000 plus 6,000. I got 4,000 cubic centimeters. Is this okay? Can anyone confirm the 4,000?
Yep.
Okay, thank you. Okay, so I know we only have 3 minutes, so maybe we should talk about the test.